Hello everyone, I am Deep Patel from LJ Institute of Engineering and Technology. Today we are going to start our new topics of chapter number 3. First we will prove the equation of Cp minus Cv is equals to R, that is also known as Mayer's equation. So first of all we will derive this equation, that is Cp minus Cv equals to R. Second, we will discuss about the flow processes and non-flow processes. Then we will discuss about the STP and NTP. STP is the standard temperature and pressure, NTP is the normal temperature and pressure. Okay, so these are the three topics which we are going to discuss today. So first of all, we will start with the Mayer's equation, that is the Cp minus Cv is equals to R. Okay, so first of all, here we have to take some assumptions. Okay, so here we will take that the mass of the system is 1 kilogram. Then we will take two conditions, that system is changing from position number 1 to position number 2. Okay, so here at position number 1 there will be some temperature, that temperature is T1, and there will be some temperature at condition number 2, that is the temperature T2. Similarly, at condition number 1 pressure will be P1, and at condition number 2 pressure will be P2. Similarly, volume V1 and V2. Okay, now if here we take case number 1, that is the constant volume. Okay, now here you have to remember that we about the specific heat. We have discussed about the specific heat in our previous lecture, that the specific heat means the heat required to change the temperature of unit mass by unit degree Celsius. Okay, and if we take specific heat at constant pressure, then it is indicated by Cp, and specific heat at constant volume, that is indicated by Cv. Okay, so if we measure specific heat at constant volume, then we can write it as a Cv. Okay, so in the case number 1 we will take that heat interaction is taking place in the constant volume. Now the constant volume means the volume will not change, so the system boundary will remains as it is. Okay, and if the system boundary will not change, then there will be no possibility of the work taking place. Okay, because we know the equation of work done is equals to P dV. dV is the change of volume. So if the volume is not changed, so the work done in the control volume is equals to 0, because change of volume is equals to 0, W equals to P dV, and dV equals to 0, so W equals to 0. Okay, so for the control volume, work done equals to 0, that you have to remember. Okay, so heat supplied at constant volume, we can write mCv T2 minus T1. Okay, here why we have put Cv, because here we have supplied heat at constant volume. Okay, now if we write first law of thermodynamics, then we can write Qv, or heat supplied at constant volume, is equals to du plus del W. But for the control volume, del W equals to 0, so we can write Qv, heat supplied at constant volume, is equals to du, that is the change of internal energy, is equals to mCv T2 minus T1. So what is the meaning of this equation? Okay, so if we supplied 100 kilojoule heat into the control volume, then the whole amount of 100 kilojoule will be stored as in the form of internal energy. So here you can write Qv equals to du, that is the stored energy. Okay, now our next case is the heat supplied at constant pressure. Okay, so if we write heat supplied at constant pressure, then we can write Qp is equals to mCp T2 minus T1. Here we have write Cp because we are talking about the heat is supplied at constant pressure. Now in the constant pressure what happens? Here the boundary will not fix. Okay, so boundary can be movable, and if the boundary can be movable, then there is a chance of work done. Okay, because we know the W equals to PdV, boundary will be changed, so the volume will be changed, and ultimately there will be work done in the constant pressure process. So if we want to write first law of thermodynamics for the constant pressure, then we can write Q equals to del U plus W, and W equals to PdV, and del U equals to mCV T2 minus T1. Okay, so here we can write the equation that if we supply some heat at constant pressure, then that amount of heat will be used into the will be classified into the two categories. First, the some amount of the heat will be used to increase the internal energy, and some amount of the heat will be used to do flow work, okay, or the work done. So here if we supply 100 kilojoule heat, then some amount of heat will be used to form internal energy, and some amount of the heat will be used to do work. 60 kilojoule of heat will be stored in the form of internal energy, and 40 kilojoule of heat will be used to do flow work. So this is how heat interaction in the constant pressure process is divided into the two categories, internal energy and the flow work. Okay, that is the PV2 minus V1. Okay, so we can write that heat supplied at constant pressure equals to del W plus du. Okay, so here QP we can write mCp T2 minus T1, del W, that is the work done, is equals to P V2 minus V1, and change in internal energy is equals to mCv T2 minus T1. Okay, now here we can write PV2 is equals to MRT2 and PV1 equals to MRT1 according to the characteristics gas equation that we have discussed in our previous lecture. Okay, so here you can write mCp_T2 minus T1 is equals to MRT2 minus T1 plus mCv_T2 minus T1. Okay, so here you can easily see that here m is common, so m cut. Okay, T2 minus T1 is common in the left hand side and right hand side, so it can also cut. So finally what we get, Cp is equals to R plus Cv. So finally we can get the relation that Cp minus Cv is equals to R, or we can say that specific heat at constant pressure minus specific heat at constant volume is equals to characteristics gas constant R. Okay, and this equation is known as the Mayer's equation. Now our next topic is the flow process and the non-flow processes. Okay, so first of all, flow process. Flow process occurs in the system having open boundary and permitting mass interaction across the system boundary. Okay, and the non-flow process means the process occurs into the closed system in which the mass interaction cannot be possible but energy interaction can be possible. Okay, so let us take one example to understand what is the flow process and what is the non-flow process. Okay, so first of all we will discuss about the flow process. So if we take one example of the nozzle, in the nozzle what happens, the steam enters from the one section and steam is going outward into the another section. So during this time what happens, the mass interaction is taking place because steam enters and steam is leaving, so mass interaction is taking place. Also with the mass some energy interaction is taking place because from the nozzle there will be some heat transfer. Okay, so energy interaction and mass interaction both is possible in the case of nozzle. Okay, if we take second example of the pump, in the pump same type of mass transfer as in the form of water is taking place and the energy transfer is also taking place. So this kind of processes are known as the flow process. Okay, now in the non-flow process what happens, the mass interaction cannot be taken place but only the energy transfer can take place. So if we talk about the air conditioner, in the air conditioner we fill refrigerant for the one time, then the amount of refrigerant will remain remains as it is, but there will be the energy interaction is possible in the case of the refrigeration and the air conditioning. Okay, so this type of process is known as the non-flow process. So in the non-flow process, mass transfer cannot be occurs, or mass will remains constant and the energy interaction can be possible. So in this chapter we have to discuss about total 5 types of non-flow processes. Okay, so the first is the constant volume process. So constant volume process in which the volume will remains constant or the system boundary will not change. Okay, so that we will discuss in the constant volume process, that how the heat interaction, the energy changes occurs in the constant volume process. Sometimes this process is also known as the isoporic process. Then the second process is the constant pressure process. In the constant pressure process, we will discuss about the how heat interaction taking place in the constant pressure process, how the work done can be takes place in the constant pressure process, energy transfer, enthalpy, all we will discuss in the constant pressure process. It is also known as the isobaric process. Now third one is the constant temperature process. Okay, in the constant temperature process we will discuss about how we can maintain the constant temperature and the process can be takes place. Also we will discuss about the work interaction and the heat interaction in the same process. Okay, sometimes this constant temperature process is also known as the hyperbolic process. So why it is called hyperbolic process, that all we will discuss in the constant temperature process. Next is the adiabatic process. In the adiabatic process, heat transfer is zero, no heat transfer can take place, so that we will discuss. Then in the adiabatic process we will also discuss about the adiabatic law, that is the PV raised to gamma equals to constant. So all that we will discuss in the adiabatic process. Then the last process is the polytropic process. So polytropic process is the real process in which we will discuss about the how the real process will be taking place, and for that we will discuss about the polytropic law, that is the PV raised to n equals to constant, and in the polytropic process how heat interaction, work interaction and the energy interaction taking place, all we will discuss in the polytropic process. So these are the 5 topics that we have to discuss in our next lecture. Okay, now our last and the third topic of today's lecture is the STP and the NTP. Now what is the STP? STP is the standard temperature and pressure. This is the one condition in which we put some value of pressure and temperature, okay, as a constant, that is the standard value. So for the STP condition we can take pressure as 101.325 kilopascal. Okay, that is the 1 atmospheric pressure, and the temperature is 25 degree Celsius. This is the standard condition, this is the fixed value for the STP. Okay, now second is the NTP. NTP is the normal pressure and temperature, and for the NTP condition we take some constant value of pressure and temperature. Okay, so for the NTP, the value of pressure is same as STP, that is the 101.325 kilopascal or 1 atmospheric pressure. Okay, and similar, and the temperature value is changed. Temperature value is 0 degree Celsius. So here the value of temperature is changing compared to STP. In the STP the value of temperature is 25 degrees Celsius, and in the NTP the value of temperature is 0 degrees Celsius, but the pressure will remains same as it is. Okay, that is the 1 atmospheric pressure. So in the today's lecture we have discussed 3 important topics of chapter number 3. First is the Cp minus Cv is equals to R, that is the Mayer's equation. Second is the what is the meaning of flow processes and the non-flow processes, and we have to discuss total 5 non-flow processes, that is constant volume, constant pressure, constant temperature, adiabatic and polytropic process. And in the last we have discussed about the STP condition and the NTP condition. Okay, so thank you for today.